industry is continually looking for new materials to offer stronger and more reliable performance, but the next game-changing development is expected to be graphene. It's a substance that's long been theorized to exist, but has proven to be so complicated to manufacture that it's taken until now to become feasible. As the name would suggest, it is derived from graphite, which is the material you'll be familiar with that's used in pencils. Made entirely from carbon atoms, graphite is a three-dimensional structure. But the exciting thing about graphene is that it's two-dimensional. What this means is that the carbon is arranged perfectly in a hexagonal honeycomb formation that's only 0.3 nanometers thick, and there's just 0.1 nanometers between each of the atoms. It's also 200 times stronger than steel, but 6 times lighter. It's almost completely transparent because it only absorbs 2% of light, and it's impermeable to gases, even the lightest ones. And it can also have chemical components added to the surface to alter its properties.
But what if you could turn something like this into something like this? This idea kind of reminds you of Mr. Fusion from Back to the Future. But scientists at Rice University have developed a method for turning virtually any material into valuable graphene. Now, if you're not familiar with graphene, it's been dubbed a kind of wonder material. It's essentially a thin layer of graphite, but it's one of the strongest materials in the universe. In fact, it's 200 times stronger than steel. All right, so how do you make this wonder material from trash? Well, Professor James Tour and his team start by placing the source material, which is really anything carbon-based, between 2 electrodes. Then they hit it with a short electrical pulse that instantaneously heats the material to about 3,000 degrees centigrade. The whole process takes just about 10 milliseconds. That's why Tour calls it flash graphene. The upside here is pretty staggering. Right now, graphene can cost up to $200,000 per ton. But the flash graphene process is cheap and simple. It can be done with just about any source material, not just food waste.
And the great thing environmentally about this is most of the trash that we generate as humans is made out of carbon. So we eat carbon, and all our plastic bottles and plastic is made out of carbon. And we can take now plastic waste and turn it into graphene very inexpensively for about $100 in electricity per ton.
Now, back to that cinder block. The team says by adding less than 1% of flash graphene to concrete, it could strengthen the concrete by 35%. That means less concrete is needed during construction, cutting the carbon footprint. According to Rice, cement production is to blame for as much as 8% of human-made carbon dioxide. And the environmental benefits don't stop there. Flash graphene creates a cleaner use for coal rather than burning it. And it creates a use for stuff that would otherwise just go sit in a landfill. And you might be wondering about that excess gas that's left over. Well, Tour even says that valuable elements like oxygen and nitrogen could be collected and used for other things. And because the process is so quick, it doesn't produce a ton of heat. In fact, you can touch that container with your finger just a few seconds after the flash.
This isn't an illusion or a magic trick, although it's often passed off as one. It's nitinol, a bizarre metal known as a shape memory alloy that can be trained to remember any shape. It's been slowly gaining popularity over the past few decades, but it's about to be put through one of its biggest tests yet. Nitinol is an alloy made of nickel and titanium, and was first discovered by Dr. William J. Buehler in 1959 as he was looking for different alloys to use in the nose cones of missiles. But he noticed that nitinol had a very peculiar response to temperature and stress.
So shape memory alloys are governed by this principle of phase transformation.
Othman Benifon works with shape memory alloys at NASA's Glenn Research Center. He talked us through what's going on within the metal. But some materials can also go through different phases and remain a solid under extreme temperature or pressure. The elements are the same, but the arrangements of the atoms change.
So you really don't change the matter from solid to another liquid. It's a solid to solid phase transformation.
Lots of materials have this property, but in nitinol, the process can be controlled.
And the key to shape memory alloys is that this phase transformation is reversible. That is the key. That is why we have that name memory. So you can heat and cool and go back and forth. There's always a path to go from one state to another.
To train the nitinol, you heat treat it at 500 degrees Celsius in your desired shape, then quench it in cold water. Now, whenever the alloy's temperature reaches a threshold, known as its transformation temperature, it reverts back to the shape you trained it to remember. And there's more to nitinol than just the shape memory effect. It can also be super elastic. If the alloy is created to have a low transformation temperature, say below room temperature, then it's already in that phase of its final shape. So when we try to deform it, it bounces right back. By altering the ratio of nickel to titanium, scientists can choose from a broad range of transformation temperatures for these reactions to occur. That way, nitinol can reshape or bend predictably in a variety of applications or environments. Shortly after its discovery, scientists and engineers created a nitinol heat engine, which rapidly heated and cooled a nitinol wire to drive a pulley system and generate energy. Soon, nitinol showed up in everything from the F-14 fighter jet to flexible eyeglass frames. And in the medical field, nitinol is widely used in stents that can easily fit inside a blood vessel and then expand to help treat heart disease. Since shape memory
is dragline silk, aka the spider's lifeline. Dragline silk enables the spider to hang from ceilings and serves as a constant connection to the web, allowing it to drop away if it's in danger. And this particular silk is perhaps the most remarkable material from the natural world. When it comes to its strength, many comparisons are made between spider silk and steel, and for good reason. Dragline silk combines toughness, strength, and elasticity to an extraordinary degree. But do the steel comparisons really hold up? Can this delicate, natural material really have a similar strength to the material we build bridges and skyscrapers out of? To get to the bottom of this claim, we first need to understand what the meaning of the word strength even is. There are different types of material properties that define how a material will respond to different types of stress. There's things like toughness, a material's ability to resist damage from impacts. Glass, for example, has low toughness and shatters when smashed with a hammer. Rubber, on the other hand, can completely withstand a similar blow. Then there's compressive strength, the ability to withstand being pushed together before being compressed, crushed, or buckling. And stiffness, a material's ability to resist being deformed. For properties like stiffness, spider silk is nowhere close to steel. But there is one area where spider silk particularly excels, in its tensile strength, the resistance to breaking under tension. Tensile strength is measured in pascals, the pressure of 1 Newton per square meter. And for a material that seems rather delicate, it surprisingly has a similar or sometimes even better tensile strength than steel. This means a single strand of spider silk can outperform many types of steel of the same diameter. This is impressive enough, but when you consider the densities of each material, it's even more so. Spider silk is about 1/6 as dense as steel. This means a strand of silk is much stronger for its weight than steel is. This level of strength and flexibility is essential to their survival. When an insect strikes their web, the stretching of the matrix enables the web to withstand the impact of the flying prey. Over hundreds of millions of years, these properties were favored during the process of natural selection, giving us the extraordinary material we know today.